Welcome to Chaos Orchestra Episode 3, Knowledge-infused Learning. About 100 years ago, Einstein defined intelligence as the ability to adapt. And I even like more a slightly modified version of it by Francois Chollet, who said, intelligence is the efficiency with which we acquire new skills for tasks we were not prepared for. In more technical terms, it's the ability to generalize from as few samples as possible. Humans are outperforming any AI system in generalization. However, neuroscientists like Jeff Hawkins believe that our intelligence is not a product of everything we learn, but rather we'll learn on top of a framework or knowledge that was hard-coded by evolution into our brain. And then there is things that we are taught rather than learn them by example, like arithmetics. Today we will explore one suggested way of trying to mimic human intelligence developed by the University of Carolina. It addresses two problems: generalization, but also explainability, so trying to explain the deep learning black box. The following is a conversation with Manas Gaur, co-developer of Knowledge-infused Learning, who's trying to build intelligent system for healthcare and social informatics.
If I want to convert an English into a Spanish language, right? I don't need explainability because this is a one-to-one mapping system, right? There is one input and there is one output, right? But when I'm talking about a system that is helping others, that is supporting human beings, right? That's where I would be interested in an explanations. That's where I would be actually saying that black box is not sufficient. So I don't think that black box is completely wrong. In majority of the mundane tasks which are not complicated, you are pretty much aware of those information. uh, you can have a black box system in place. But where things are like very complicated, laborious, and takes a huge amount of time, and you're given a system that does a job pretty quickly, right? But the outcome of that system needs to be assessed. That's where explainability comes into picture and opening of the black box come into the picture. Let me give you a very simple example. uh, we as a computer scientist do not do too much of bookkeeping, right? Or do not do a good of cataloging or summarization, right? Or reading an articles and making new discoveries, right? Our paradigm of research is completely different. When we look at the person who is in life sciences or physical sciences or biological sciences, their way of research is completely different, right? If I want to develop an AI system that would help them in making, let's say, doing a fast discovery of let's say research. Let's say they want to test whether these two compounds would should react or not, or whether this new material would work or not, whether this new drug would be effective or not. You are using a deep learning algorithm for drug discovery, for material design. But in these applications, simply saying that this drug would work would not be a sellable point. A domain expert would not buy that until unless he could trace back to the learning channel that you have followed and see why this particular drug was recommended, why this drug would be an effective one, why this particular material is effective, right? A very interesting example that came in the recent study was when you are looking on social media. uh, like social media has been an effective source for research for days now, right? For years now. Like you talk about fake news, you talk about misinformation, harassment, you talk about news exposure. Everything is on social media. Now when you are taking a system that would actually extract information from social media and give a recommendation, right? That whether this information is right or not, it requires some facts, it requires some observations. So what is given to the given as input to the model are observations, but there is a lot of facts out there. So the fact and observation gap is what is the story of a black box. So black box is only given the observational data, right? And data that is a kind of a representation of a very narrow population. But there is a big larger population that is running on facts. So bringing that facts into the model is what help in resolving the black box problem.
You need this explainability only as soon as you have a human in the loop, right? So before
Yes.
that, if the
system is able to resolve the task by itself, then you
Yes.
don't necessarily need to understand how, right? But as
Yeah.
soon as the human has to make a decision based on what the system gives you, then you need explainability.
Right, right. And I have seen some new workshops, research directions taken by JP Morgan and IBM Research and many other institutes, many other organizations as well, on financial side as well. So there's a financial decision making where they are making sense of the predictions by using the logs, the financial logs that they have, right? So they have this entire documents which they convert into an ontology which helps their their decision making process, right? Another example is basically your purchasing behavior, your transactions, your expenditures, right? I can actually give you a better recommendation if if I have a knowledge of some other person who's of the very similar kind in expenses and in transaction as you are, and I would be able to recommend you a better deals by using his knowledge. So if I give a model only about you, I cannot diversify my recommendation. But if I have some information outside the box coming into the picture, the diversification comes into play. And that's another reason why black box needs to be opened, because a black box system is only driven by a small sample of data, a data which is not representative of a larger audience. And if I bring another a world model, what say we can say, or domain model, if we say, right, is augmented to the deep learning model, that's where you are opening the black box. You're giving it a wider horizon to explore, right? And I would actually suggest people to read about an article which is very old one. It's called uh, a romance of Flatland. It's basically like it's the book name is Flatland, which we call it the Flatland romance of many dimensions. It says that every dimension that you add to your model should have some significance, right? And until unless that significance is not coming up, right, the model is doing something you are not aware of, right? So until, so let's say like I need to be very conscious in what I'm giving to my model, and the model should be very much conscious of what it should include and what it should not include, right? So I would say that black box theory is also from the side that if I'm aware of what my data is going inside, I know what the model will do, right? But if I do not know what my data is and I'm giving my model to do something, the model will anyways will do something, will give an outcome, but that outcome cannot be explained because you do not know the resource that can explain that outcome. So that's the whole story of a black box. Suppose you are giving an exam, right? We are giving an exam. Let's say we are like a 12 like a K-12 students. There's a K-12 education system, right? And you are given a question and you're given an answer, right? You have given an answer to the question, and this exam was submitted. Now you recall your answer, right? You have your answer in your mind, and you go back home and you check in your books whether my answer was right or wrong, right? So you are actually doing a kind of explanation to yourself that whether my answer was right or wrong, right? Now model, take the model again. You're giving a model data and the model gives an outcome, right? You check that outcome and you pick that outcome and you check on the Google, you check on your books that whether this outcome makes sense or not. Oh, it makes sense. Now that's formulate your discussion, right? That I know now, I know what I need to make a discussion. But in this process, right, there is a human labor involved, and this is what they call it as a post hoc explainability, because you are doing an explanations over the outcome of the model, right? So this has been a very known phenomena in the past research, where they people have done unsupervised learning or supervised learning, and they got an outcome, and then they validate that outcome with the help of a domain expert, right? For example, there is a prediction that is being made in healthcare, or let's say if I classify a particular news as a fake news, right? About, or for example, let's take an example of very known, which people might very well be aware of, the Boston Marathon bombing, right? There is a whole story about it that the death of the majority of the people came from the suicide as a consequence of the marathon bombing. There was a psychological impact. Now, if a model is put into place, the model will be judging an outcome based on the marathon bombing incident and not exactly on the suicide, right? So we want to see, now the model gives an outcome which is somehow good enough, and what you do is the outcome you take, the outcome you have received from the model, you check it on the news agencies, you check on the social media, that, and you confirm your story that, oh yeah, model did a decent job. That is where post-hoc explainability has come into the picture so far, right? And people have done this a quite number of times. And let me give another recent example. There is an example of autonomous driving where Bosch is exercising a lot of efforts. For example, that suppose you are driving in Colorado, right? And I have a picture of Colorado in my mind, and I have given that scenic area to the model. The model is learning the driving scene is pretty good. Now you want that model to work well in California, right? Which is, there is like little similarity in the scenes, right? There are mountains, there are hills, right? There are shops, and there are schools and everything, and you want the model to do a pretty good job over there. So how are you trying to do an explanation? So you are getting an explanation that model is doing some behavior over there, and I'm checking the similarity between the area where the model is working, where this autonomous driving vehicle is working, and where the Colorado's job was done. And if there is a similarity, I can say, yeah, model is doing pretty good. So you are not checking the explainability as the model is learning. You are doing an explanations on the top of the model's outcome, right? And this has been a kind of a exercise, because getting explainability inside the model is still complicated, right? Because it goes through a very different turf of loss functions and optimization function changes. But a post-hoc explainability is a very doable task, and it gives us sufficient confidence on the outcome that the model is actually learning what it's supposed to learn. And I think that that's where attention model does. There is, I would say that there is two contradictory papers. One paper that says attention all you need, and the other says attention is not all you need. So the paper that says that attention is not all you need is a machine translation paper, right? You don't need a you don't need a knowledge for that, right? Attention is needed for a domain specific task. So the idea of an attention model is pretty interesting, that it gives you an it doesn't tell you that check the model's outcome. It says that check the weight matrix, right? I have given you a kind of a heat map visualization over your input. Just check with your resource whether this visualization makes sense or not. That's another example of a post hoc explainability. So yeah, along that line, there is a significant amount of research. I would not say it's not achievable. It is definitely achievable, but the concern is that on resources. So one thing that Boris, I have seen in the past is that when people do their job, their research on social media, or they do their job on a social impact domain, people try to utilize domain experts as annotators, as evaluators. Let's say Amazon Mechanical Turk, right? People consider Turkers as annotators. They annotate the data. They get the data annotated, and they train their system, right? What I was thinking is that, why do you want a domain experts to be an annotator? You want the domain expert to be a supervisors of the system, because they are the people who will be using your system. So there is a shift from annotators to a supervisors. There's a recent pretty nice work by Harvard University, by the lab by Professor Milind Tambe. uh, uh, they actually did a lot of good job in kind of a contextual bandits, which is a reinforcement learning paradigm, where they actually made some rules to to reason over a very complicated domain. Let's say poaching, and or there is another work on illegal fishing, where you cannot expect model to learn the entire domain, and rather you give the model some rules over which it will learn, right? So what I was thinking that you gave the model the data, the model that the data is having, and you get the you develop a model, a very simple one, not a complicated one, right? Let's say I'm talking about an integer linear programming in a very simple sense, which is a mathematical optimization framework. It has constraints, it has rules. Rules are governed by a knowledge graph, and constraints are also given by a knowledge graph. Or these constraints and the rules are given by some resource, let's say a book, right? Or a lexicon, right? Which is a flattened version of a knowledge graph. Because I'm hiding all the relations, I'm just only focusing on the concepts, right? And I'm trying to make a prediction, and the prediction comes in. Now the domain experts will take the prediction, will learn the trajectory that the optimization function has taken, which can be easily analyzed in terms of the chain of the concepts it has traversed, and can relate pretty well that whether this came by chance or it is a thoughtful process, right? So that kind of an integration is what is needed uh, nowadays. I find that people have worked terrifically well and about through Lime, which is a local explanations model, Shape, which is another representation model for representing the different behaviors of the model. Let's say there's another work by Facebook knowledge on knowledge distillation, where you say that I learn a weight matrix of a very gigantic model and use that to solve a small task. But in all this process, one thing is very missing, that you are still leaving the task at the end user to judge, to verify whether the outcome is right or wrong. Where I'm saying that in this process you bring them into the loop. You want the people to be a supervisor of the system. They know what is a chain. I don't want them to look at the optimization function or loss function. I want them to look into the change in the concepts that's happening over the time, right? And check the outcome, and then should relate them together to say that what went wrong, or did the model went sideways, or did the model learn a wrong concept, or am I missing something that model did very well, right? Because it's all about exploration and exploitation of the search space in the artificial intelligence paradigm. And we want the knowledge graph and the model to work together, so that first of all, the biggest benefit that you will get is that you don't need to make some heuristic thresholds. You cannot say like I did a zero point 0.6 threshold or zero point 0.7 threshold or zero point 0.8 threshold to solve the problem. So the threshold over here is governed by some facts, right? And you say that if I'm going very far away from that required information, that's where I need to penalize the model, right? And if I'm going too specific to the problem, that's where I want to threshold the problem. So that too far and too less is what you're governing by your knowledge graph, and that's where I would exercise my research towards to.
So you're basically saying that the expert is responsible for the governance of the model that learns by creating a framework that it's learning that it's by creating a framework that the learning is based on, right? So
Yeah.
the framework is basically defined in the knowledge graph that contains all the rules and constraints about the domain to make it easier for the system to learn basically.
Right.
How much of this knowledge graph of these rules and constraints is needed? So how much easier is this supervising than annotating?
Yeah. So first of all, in the annotation, right? When you're doing an annotation, you pick, let's say I pick 40,000 samples, 50,000 samples, 60,000 samples, right? And I annotate it, right? Uh, how can I believe? How can I first question is, how can I verify that my sample size is an adequate sample size for the domain coverage? I'm talking about, let's say, the domain of fake news, right? Or if I'm talking about the domain of financial decision making, and I did my decision on, let's say, 40,000 tweets, or 40,000 samples, or 40,000 logs of financial records. Does that 40,000 record give me a complete picture of the audience? I'm not sure about it. So when I'm doing an annotation and I'm saying that okay, this model works well with this 40,000 samples, Can I say the model will work on a 1 million sample? I'm not sure, right? Whether this if let's say an outlier come into the picture, I'm not sure how much outliers I can handle, right? I'm not sure about the things that this sample is. Let's say there are millions of concepts. Let's say financial decision making is a huge gigantic field in itself, right? People have been in financial decision making for almost decades now. There are new concepts, new theories, new adaptations comes every year, every month, right? Research happens over there as well. Now if you take a small sample of it and you train your model, there is a part of this whole section that is untapped, right? You are not aware of those informations, you are not aware of other behaviors, right? Suppose you are talking about, let's say I'm talking about a company known as JP Morgan. So JP Morgan built an AI system localized to their own financial records. Maybe there is some information out there on social media that can be exploited to help that decision making work better. How can I bring that information into the model, right? So that is not annotation. You cannot annotate millions of records, you cannot annotate billions of records. So annotation is kind of what do you call it, is constrained by the capability and the time that it consumes. Whereas if you now, after that, even after giving a very high quality annotations, let's say 80% agreement, you're still not sure that the model will learn the very details of it, right? And Boris, I want to bring a very interesting concept that I like about uh, pack learning, which is a concept known as probabilistically approximate correct learning, which is an old phenomena. It, I think, dates
What's up?
probabilistic approximately correct learning, PAC. It's a, I think, 1980s phenomena. It says that in order to get a good results, which is, what is a good result? That is, the training error is zero, right? And testing error is nearly coming to zero, right? So that's what you want. But for that, you need millions of samples and a very complicated hypothesis, right? Because these things doesn't come easily. A very simple example was the neural net XOR case, right? It was able to classify and, it was able to classify or, but things went sideways with XOR, right? XOR gates, right? That's why multi-layer perceptrons came into the picture, right? Because you want a big complicated hypothesis to solve non-linear problems. But this complicated hypothesis requires more number of samples. Now, there's a trade-off. How do you build a complicated hypothesis when you don't have the training sample that long? And if you have a very big samples, how do you actually define the complicated hypothesis? You cannot simply say that I will use BERT or any model without thinking whether that model will work or not in this domain. So before now, first of all, you do annotations. Annotations are incomplete, right? They are not of good quality. They do not represent a larger population, right? And then you actually utilize a model with some heuristic bounds, heuristic thresholds, and you come up with an outcome, right? But this, now in this entire paradigm, first of all, the input is not complete, the model learning is not complete, right? The model is approximating, it's not learning, it's, I would say, it's learning over the data, not learning over the task, right? And it is giving you an outcome which you cannot even verify whether the outcome is right or wrong. So at every stage there is uncertainty, right? And in this uncertainty needs to be resolved, right? So one thing I'm pretty much sure that there is abundance of data out there in the world, right? I do not want to annotate all of them. I don't want to annotate any one of them. I want to do, what I want to do is, that data is actually coming from some resource, some knowledge, right? Suppose I'm making a research paper, I'm writing a research article, right? For that research article, I need to think, I need to process my mind, and I need to then jot down the process of what are the points that I will be covering in that, and that's how I write my research. So these conceptualization is already available in DBpedia, in Wikipedia. You do Google search to write an article. You search Google Scholar for an article. right, and get more information. So this information is already available. Now this information where you want to utilize this model, and this fact of information where this information is already curated and stored, you want to bring them together. I want this structure to label this, right? I want this knowledge graph, let's say questionnaires or things that the people have already categorized, which they call entity classes, right? Those entity classes can actually help me label these this enormous huge data, and I give this the model. The model will require some sort of knowledge, because that's how I'm labeling it, right? This is kind of a triangle, that this is the model that is what is to be trained. It takes the input of the data which is already labeled by this resource, and this resource also goes into the model as a helping hand, right? And the outcomes comes in. The outcome is checked by the domain expert with this resource, not with this data, with this resource, to check whether the outcome is making sense or not. And this becomes a kind of a expert in the loop system, which is also in Stanford's recent initiative, which we call it human allied data science, right?
Do you think humans actually also learn based on a framework?
Yeah, definitely, because I have a limit to my exploring phase, right? I cannot explore all the possibilities, but model does. Model can explore all the possibilities. So what I can do is I can just validate that whether this potential outcome is a valid outcome or not.
So there's this example of autonomous driving, right?
Hmm.
So we have many car accidents are happening in the world,
Hmm.
but we are more likely to read about the car accidents that are happening because of an autonomous system steering the car, right?
Hmm.
So we have very high standards and requirements for AI
Hmm.
that is much higher than for humans.
Yes.
And can explainability, right? So understanding the biases of a system and understanding the circumstances under which the systems work well or doesn't work well, can that help to resolve this problem?
Absolutely. So I would say that like a traditional artificial intelligence was constraint satisfaction, right? The hill climbing algorithm, the A star algorithm, AO star algorithm, right? These are all like have constraints in it, right? They have rules, right? And they are some kind of, let's say, a length based constraint, for example, right? Word based constraints, right? So these constraints, like, I agree with you, like in the autonomous driving vehicle, there has to be some constraints, right? The constraints can be let's say I'm driving in a school district or a school lane, that there's a chance of a ball coming in all of a sudden. There's a chance of a children crossing from, let's say, not on the pedestrian area but maybe somewhere on the road, right? There can be children, there can be like a school bus standing somewhere in the middle because it has to pick and drop us children. So like there are many possibilities of the scene, which makes them very specific than different from the others, right? Another example can be, let's say, in a shopping mall, right, or a shopping area where the cars can come from either side, right? And you can have, yeah, the parking is open to all. There's no particular lane where you can need to go to and go and park the car, right? And the behavior, I'm taking another example, the behavior of a downtown, in a downtown city, which are pretty old infrastructure. They have a different way of driving, right? There the parkings are on the street straight away. There is no particular parking area. So you need to be aware of that. Okay, the person can come all of a sudden, a person can open the door, right? There can be a blink of a light, let's say a faulty indicator is on, that needs to be captured by an autonomous driving vehicle. So all these scenarios are independent, right? There is some in all they are independent, but there is some kind of a concepts which are common. So the model needs to learn some of those things, those common concepts, and needs to learn over the domain specific concepts as well, right? So that's where actually the main question is, that there are things that the model can easily learn because they are common, and the things which are very domain specific, which you need to give to the model as rules, right? So
It doesn't just become transparent, but it also needs less data. and
Yeah.
can reason over based on the knowledge graph over the data we gave
Yeah.
it.
Because this behavior of school district, right, this behavior of schools, the roads which are where the schools are located, are pretty much same throughout the country, right? Every behavior will be same. Students can school, the children can come all of a sudden, they can be playing on the street, on the ground, and the ball comes all of a sudden outside on the field, on the road. So these behavior are you can say these are generalizable. You can generalize over these things. So I would say like autonomous driving vehicle is perfectly an appropriate application where you have common sense and domain specific constraints and rules to basically to act more consciously and with explanations and interpretations, rather simply, because I think over there's nothing like yes and no. There is something that you act upon, so there is more like a structure in your prediction in autonomous driving, and that's where I think a perfect area of explainability and interpretability comes into play.
So this knowledge infusion is basically providing the model with some common sense knowledge
Yes.
to make it more efficient and more explainable. Now, at what stage do you infuse this knowledge? Is it do you do it before you even start providing some data, or can you even do that later in the process?
So there that's actually a kind of a like a classification that we came up with, known as shallow infusion, semi deep, and deep infusion. uh, so there the reason where is that the knowledge, as I said in the previously in our talk, that uh, when we are actually utilizing our data to train my model, right, the data is not a representation of a larger population, right? I need, and data can be very messy as well, right? Because trust me, Boris, and people never thought about it, that a data would actually can be learned. There's no there was no preconception in the mind of the people that there can be a world of artificial intelligence which can simply learn over a massive amount of data and make some predictions, right? So the data that was created was in a human unconstrained natural language, or unconstrained languages, or maybe some records, maybe some cataloging. We came up with this data is already there, right? But it is messy. It has never been curated that much because it consumes again a lot of time. And if you put it into the model, then again the question of explainability comes into the picture, right? Or the black box nature comes into the picture. We want, and another challenge is, apart from the messiness, the things which are very much important in decision making are always few, right? For example, if I ask you to explain me a very complicated concept, let's say, or a very simple concept in a finance, right? Your definitions would be more of like the main entities will be very few in that in your definitions, and you many other function words would be very much high, or modals would be very high in your words, right, to make a sentence. As a consequence, when you put this into the model focuses on high frequency words, very high, because they are occurring very large in numbers, right? We want the model to direct it towards the concept which are very much important into the decision making side, right? That's where we want to bring the knowledge. So we want to populate we want to change the input using the knowledge, so that less of the function words are present and more of the concepts related to the decision making are present. Definitely there's a disadvantage to do it. That disadvantage to it is that the grammatical correctness of the data is lost, right? It goes haywire. But the prediction works pretty well, because now model doesn't need to focus on those individual words, because you replace them with the major concepts. So this is an infusion of the knowledge at the initial stage, right, where you enrich your data with some context, right? Context is a very technical term, but its context is something that any information that is not present in your data but came outside from the data, but you know that the information is correct, right? It's kind of an implied things, right? uh, Again, now another thing is that, okay, this is one way where you want to infuse the knowledge. Other is when you want to learn within the model, right? In that case, things becomes very important as well as challenging as well, because consider this thing, right, Boris, I'm actually talking to you, you're listening to me, and I'm speaking. After some time you will be talking and I will be listening, right? Your questions I will be listening and I will be giving my response. So there is a exchange of thoughts. You are saying something that I will be comprehending, understanding, and then responding with a response. That's what the inner structure is, the model, right? The model is given an input, the model needs to learn something and gives an outcome, right? So there's an interaction between the data and the model. The data is a person who is giving the information, and the model is comprehending it and giving an outcome, right? The outcome can be a person, or it can be a data, it can be a human being altogether, right? So there is this channel, right, happening. This comprehension is complicated because with a limited set of information you cannot expect the model to do miracle, right? So attention is something that attention tells you, okay, don't focus on everything, just focus on the things which are important. Now attention doesn't know which word it should focus on, so it will focus on the function words or periphery words, because it goes by the concept that a word is known by the company it keeps, right? A word's importance is coming by its neighboring words, right? So we want to change this philosophy by saying that we will add some knowledge, a calculated knowledge, into this model, into this attention matrix, where the attention is governed by some kind of a concepts in the knowledge graph. How do we do it? Is that we we learn a mapping between what the model is learning from the input data and the knowledge graph. So assume this to be an encoder and decoder, right? The encoder is a pure machine learning model, right? And decoder is a model which is learning over a knowledge graph. Now there is a weight matrix that this model will learn over the knowledge graph, and there is a weight matrix that this model will learn over the data. And what you want to do is you want to find a match between these two weight matrices, right? So you are saying that I'm saying that this weight matrix and this weight matrix will have some similarity between them. Very traditionally, this goes with the very old phenomena of machine learning and artificial intelligence, saying that every model works on correlation, right? Causation is a different phenomena. I don't want to go into the territory as of now, but I just want to keep it to the correlation formation. So correlation is basically the weight matrix that the model will learn over the data, and there's a correlation matrix that the model will learn over the knowledge graph. This weight matrix will be square because you are only within that one domain, and this will be another square matrix will be in the another domain of the knowledge graph. Now when you want to match these two correlation metrics, that's what it is, a cross correlation matrix, because now you have a different row and a different set of columns. The columns are the concepts and the rows are your concepts, and rows are your terms in your data set, right? And you want to find a mapping function. This weight matrix is can be visualized as an attention weight. Now you're putting an attention over the concepts in the input based on the knowledge graph, and you refine your attention and makes a prediction.
So imagine one day we will be able to establish a seamless connection between the domain expert who is supervising these models, and these models becoming very smart, transparent, and explainable.
Mm-hmm.
What opportunities are there? What can we do with that? So what will change in the usage of AI?
The use of human knowledge will play a very significant role in various applications, not only in social good, I would say, in many other applications which impact humanity in some sort, right? For example, a very interesting example that I can come up with is that uh, about the pandemic, right? We all know about COVID-19 situation, right? And you all know about the term which recently coined was non-pharmaceutical interventions. Let me give it a more concrete definition. These non-pharmaceutical interventions are your business closure, lockdown, school closure. Those activities are non-pharmaceutical, right? Because they are defined to control the pandemic. Now what happens is that if I'm having an SIR model, an epidemiological model which makes a prediction over the likelihood of an infected cases, it would give a very generic answer, irrespective of where it has been deployed, right? But if I say Denmark has a special policy, very specific to the people, right? Let's say Germany has a different policy, very specific to people. That specific information is what the model needs. That behavior is what the model is needed, right? For example, let's say you can take an example of India, let's say, right? India was not in the list of COVID-19 pandemic. It suddenly came into the picture all of a sudden, and there are many gatherings that took place in the middle. For example, there was a gathering known as Tablighi Jamaat movement, right, which is a movement of like some workers, right? uh, that gathering was what happened during the pandemic times. People might have exchanged some like specimens of COVID-19, and they became infected, and then they went back to their places, and they affected other people as well. Now if an SIR model is there without taking into account this movement, this gathering of information, it would give a generic prediction, right, which say that the estimated rise in the infected cases is X% in 2 months, right? But that X% came in like less than a month. Why? Because this environmental phenomena took place. And that's where I would say that this knowledge component is very critical to be included in the statistical learning, so that the prediction is not only timely, but it gives the end user an authority to make a conscious decisions over the outcomes. People are actively driving towards explanations, right? There's a huge body of research on responsible data science, accountable data governance, right? Data ethics, biases, right? For example, let's say when you are using a domain deep learning model, there is a deployment bias, there is a representation bias, there is a what you call a measurement bias, right? Historical biases as well, right? These all, like, people are actually actively involved in this. But one thing that I've found missing is the use of knowledge, the use of human knowledge. uh, that's where I would put a thrust on in my research, and in the work that I learned from other people, is that this human knowledge is already curated, it's already stored, and it's already available for use. The idea is that we want to make models that would learn things that this data, this knowledge doesn't have, right? And what this knowledge have, just bring it as it is, right? So it reduce your computation time. You do not want to compute over information that is already available to you, right? That's where I would bring in, I would say, like, it's kind of a knowledge augmented training, right? That's, I would be the right term to use, and it will help not only the explainability but also in the interpretability of your model.
Knowledge augmented reading. I like that.